Okay. The stage is yours.
Okay, so first of all, I would like to thank you for organizing this symposium on directional statistics and for inviting me to participate on it. So in this talk, I'm going to present a joint work with Eduardo Garcia Portugues, and this is about density rich estimation on the polysphere for analyzing hippocampus shapes. So this is the outline of this talk. So in the first part of the talk, I'm going to introduce the formal and the intuitive definition of what are density rich. Taking into account that density rich depend on the density function and that the goal of this work is to estimate the density rich for data on the polysphere. So before going into detail in the problem of this work, so first we are going to introduce a density estimator for this kind of data. So in the last part of the talk, we are going to, if we have time, we are going to check the performance in practice of the density rich estimator just through simulations. And finally, we are going to apply the procedure to a real data set containing the hippocampus shapes. So first, what are density reads? So the density reads provide us information about the main features of a density. So the density reads are like a dimension reduction technique, which is based on the density F. So it's like a first principal component curve. Here in this plot, you can see, I mean, some examples of population density reads. So here, with these red points, we can see the main mode of variation of these three examples. So the formal definition of what are density rich is provided in this slide. So density rich of a density F is defined as the set of points such that the projected gradient, the norm of the projected gradient is equal to 0, and such that the eigenvalues of the Hessian matrix of the density function F are negative. I mean, except the first one. So notice that a point belongs to the density rich if and only if the gradient is null or if the gradient is parallel to the first eigenvector of the Hessian matrix F. So here in this plot, we have from left to right the first eigenvector, we have the second eigenvector. Here we have the gradient of F, and here we have the projected gradient. So here we are assuming that P is equal to 2. So notice that the density rich is defined as we have said before, as the point such that the norm of the projected gradient is equal to 0. That is when the norm of this projected curve is equal to 0, and such that these eigenvalues are negative. Or as we can see here, I mean, we have that a point belongs to the density rich if and only if the gradient is 0 or if the gradient is parallel to the first eigenvector. So this is the formal definition, but how to compute the density rich in practice? So if we want to determine if a point belongs or not to the density rich, what we have to see is, I mean, we have to flow with the density, with the projected gradient until obtaining that the norm is approximately equal to 0. So in order to deal with this problem, as it was proposed by Genovese and co-authors, and also in this book of Chacon and Duong, in order to deal with this issue, what we have to perform is an Euler algorithm. So in this algorithm, we have to start with a point and then iterate until convergence. So in the interaction, notice that we have to consider this parameter 8 and also this normalized gradient. So this gradient boosts pacing through low density regions and slows pacing through high density regions. So here in this plot, we have the same example that we have introduced in, the first slide, where we have how to compute the population density reach. So here in blue, we have the points that are discarded because here we have low densities, and here these black points are the valid ones because we have here high density. So and here with red, we are indicating the endpoints of this Euler algorithm. So this is the case that we have that the density is now, that is the population density rate. But what happens with density F is a noun. So notice that taking into account the definition that we have given for F, for the density rate, this density rate depends on the gradient of F and also on the Hessian matrix of F. So depending if F is noun or a noun, notice that we have to take this into account. So in the case that F is a noun, what we have to make in that case is to replace the density F with an appropriate density estimator, such that the kernel density estimator. So if we are considering a kernel density estimator, notice that here we have to select this vector of bandwidth, and after that we have to follow as we have made before. That is, we have to compute the gradient, we have to perform the composition of the Hessian matrix, we have to compute also the projected gradient, and finally to make the Euler algorithm. So notice that in this case, we have to deal with some practical challenges, such as we have to filter some spurious endpoints, and accounting that we are using a kernel density estimator, we have to select an appropriate bandwidth 8. So this is the brief introduction of what is density rich, but recall that the goal of this work is how to deal with the density rich estimation, but in the case of the polysphere. But before going into the density rich estimation, accounting that we have to in order to deal with this density rich estimation, we have to estimate the density first. So what we are going to make now is to define first what is polyspherical data and how to estimate the density for this kind of data. So what are polyspherical data? So polyspherical data are points on the product of hyperspheres, and there are different examples of polyspherical data. For example, the data on the circle. So in that case, we have only one hypersphere, and the dimension of the hypersphere is equal to 1. If we have the sphere, then we have that we have only one hypersphere and its dimension is equal to 2. And in the case of the torus, we have more than one hypersphere, and the dimension of each of them is equal to 1. But apart from this common data that all of you know, we have also polyspherical data in the case of the direction of the spokes in a skeletal representation. And this is the case of the directions that we have in the hippocampus and the shape of the hippocampus. So the shape of these three-dimensional objects can be parameterized using these skeletal models. So as you can see here, skeletal models contains a skeleton which is located in the center of the object, that is these red points. We have also these boundary points, this blue point. As you can see here, we have also these spokes, these green radius that join the skeletal points with the boundary points. So as you can see here, I mean, each of these radius indicates one direction. So for this case of the hippocampus, we have 168 spokes, each of them indicating one direction. So here we have the data set related with this hippocampus, where we have 177 subjects. So as you can see here, I mean, the form, the shape of this hippocampus is different, but the skeleton is very common, it's very similar. So it makes sense to consider a common skeleton and try to analyze how is the direction from the skeleton to the boundary. So for this reason, with this data set, we have a parameterization on the polysphere is to 168. Recall that these 168 are the number of spokes that we have in each hippocampus, that is each direction. So, and how to deal with the density estimation on the polysphere? So suppose that we have a sample with a density F on the polysphere. So here we have the kernel density estimator that we are proposing. So here this C is the normalizing constant, and we have that this estimator depends on this product of kernels and also on these bandwidth parameters. So notice that in this case, we can consider also the possibility of including non-product kernels, but notice that in that case, we are not going to obtain a closed expression for the normalizing constant. In the case that we have a von Mises-Fisher kernel, then we have a known constant for the kernel density estimator, and in the particular case that d is equal to 2, we have a stable form for the normalizing constant when the bandwidth is close to 0. So, but recall that in practice, our goal, the goal of this work, is to estimate the density reach. So we know how to estimate the density, but in order to estimate the density reach, we have to compute the gradient and Hessian of our kernel density estimator. And this is what we have in this result. So in this result, we have the gradient vector and the Hessian matrix of the density f. So in particular here, instead of f, we have considered the radial extension of f, because on this way we can simplify the calculations. Notice that here we have the results in function of f, but if we want to consider the kernel density estimator, the only thing that we have to introduce here is the corresponding estimator. Notice that if we have the von Mises-Fisher kernel, then we obtain simplified versions, both for the gradient and for the Hessian matrix. It's important to mention that the gradient and Hessian density estimators are the basis just for performing the Euler algorithm in the calculation of the density reach. So we know how to estimate the density of the polysphere. We know how to estimate the gradient, how to estimate the Hessian matrix. So now we are going to deal with the density reach estimation for this kind of thing. So notice that the procedure is really similar that in the case of Euclidean data, but notice that in this case, the Euler algorithm should be adapted. So notice that I'm not going to provide a lot of details of these issues because we don't have a lot of time in this case. But I only want to make some comments. And the first one is that we have to make some modifications just for avoiding some problems with this Hessian matrix, the calculation of this Hessian matrix, and also for the computing times. So we have estimated the density reach, but now we have obtained a set without any kind of order. So in order to try to solve this problem, what we made is to introduce a multidimensional scaling from the polysphere to the real line on the matrix of geodesic distances. And this way, what we obtain is a data-driven index. We obtain these values. But now the problem is that, okay, so we have obtained this index, but we have to interpolate these pairs. So we have these real values and we have these points on the polysphere. And how to do this in practice? So what we made here is to introduce, so we compute an Araya-Watson regression estimator. And on this way, what we have obtained is a smooth index estimated reach that we call SIRE as this curve. So it's a curve obtained from the real line to the polysphere. And on this way, we define the score. So in this way, we can try to establish a score of an arbitrary point on the polysphere and on the SIRE, this curve that we have defined, as the index of its projection on the SIRE curve. So, and how to check this in practice? So I'm going to show now some simulations that we have performed just for checking the performance. So in particular, here we have the performance of the Euler algorithm. So the representation on the left is for the hypersphere of dimension 2. Meanwhile, the representation on the right we have for the product of two circles. So we have the convergence towards the estimated density reach. So in this case, we have that all points converge on the hypersphere dimension 2. Meanwhile, some do not eat in the case of the product of two samples. So the results regarding the desire and scores on the product of two hyperspheres, the dimension 2, are shown in these pictures. So in the representation, in the left panel, in the left, and central plot, we have the main mode of variation of the data. So here we are indicating with the solid points, the sample points. We have the Euler paths with these transparent curves. We have the read points that I'm not completely sure if you can see this, but with triangles. So we are indicating the read points in triangles. The black curve represents the common center. So the right panel shows the scores of the sample points on the sire, showing that the color gradient encoding the one-dimensional mode of variation, the data that we have is recovered. So once we have checked the performance in practice of simulations, we are going to move again to the real data sample that we have mentioned at the beginning of the talk about the hippocampus shapes. So the representation on the left shows the results that we have after applying this dimension reduction technique. So in yellow and green, we have the spokes with larger variation, and with the purple color, we are indicating the spokes with almost no variation. So we are observing that the major variation is obtaining in the right side of the plot. In addition, we are observing that variation is located in the bottom. So there is no variation in this part of the plot, and the main shape variation across subjects is mild. So the figure on the right shows the sample of scores, and it can be observed that here we have the corresponding density. We have that the distribution is asymmetric. So we are observing also here like a second cluster. We can identify which are the median subject. I mean, which is the median subject and which is the most extreme subject. Just taking into account which is the median score and which is the maximum score. So this particular hippocampus are showing this figure. So in the representation on the left is the most extreme. The representation on the right shows the median subject. So we can observe that the median subject is more symmetric. In addition, it's less curved than the other one. Meanwhile, the most extreme is more asymmetric and it's more curved than the median one. So just for finishing, so in this work, I'm sorry that no, it's fine. So just for finishing, in this work, we have introduced a non-parametric dimension reduction technique just for finding main mode of variation for data on the polysphere. So this procedure was based in MDS and Andrea Watson estimator. So in order to deal with the Euler algorithm, we have found a lot of computational challenges, but this helped us to find some insights for the hippocampus dataset. For more information, so you can go to this paper that is already submitted, where you can find the kernel density estimator, some asymptotic properties, and also some results regarding the efficiency, the kernel efficiency, and the bandwidth selection. This other publication is regarding the density reach estimation, and most of the results that we have presented in this talk. And thank you for your attention.